Hello guys, let's get started for today's lectures. And as you can see, the title is just statistics for machine learning. So I guess this is the first time that I'm talking about statistics in this lecture in terms of the machine learnings. And so far, the approach that I took is that, we're focusing on the machine learnings, various from like regressions, to regression to classifications. And we formalized all the machine learning problems into optimization problems. So we use like convex or CVXPy, so we can find the solutions in numerical way. And another perspective which I never mentioned so far is the statistics and the probabilities. So the machine learning is all about the data, right? So given data points or data sets, how do you do data analytics? How do you analyze? It's a statistics. So the probably like following topics going to be like PCA, principal component analysis, and like things like that. In order to have better understanding of, for example, like PCA, and I want to take some moment or take some time to discuss or talking about the statistics and probabilities as well, because that's going to be the fundamental understanding foundations for those in order to discuss the following topics. So statistics and the probabilities. I know that many of you heard of the statistics and probabilities, and of course this lecture is not the statistics and the probabilities, like not going to discuss intensively. So again, like I want to more focusing on to deliver the right insight or concepts in the conceptual level of that. So suppose we have data, data points and the models. Here, if I say model is probably vague, it's not like clear to you guys. But for example, if that's the regression problems, you have given data points, say it's linear regressions, your model is gonna be like, could be your models. So from data, somehow you guys were able to build or construct this kind of, it doesn't have to be linear regressions, it doesn't have to be linear, it doesn't have to be nonlinear, whatever, it could be regressions or classification, any model that we learned so far. Starting from data and reach to building a models, we call it statistics. From that, right? But we can have opposite directions as well. What do you mean by that? Starting from the models, we can get some data points. In that sense, probably the model is not, but in the probabilities, in the field of probabilities, we're talking about density, the probability density functions and probability, things like that. So I think the most famous example is Gaussian distributions, normal distributions, like exponential distributions, whatever. And again, it's okay that you never took the probability or statistics course or lectures. It's totally fine. So don't worry about it. But at least here, I want to take some moment to deliver the concepts of statistical probabilities. So in that case, the probability density functions, and the simplest probably is like Gaussian distributions. In here is the simplest one in 1D, one-dimensional space. Probably you can extend it to, you can think of other probability density functions, and also you can think about like high dimensionals, things like that. Suppose we have that kind of model. Suppose we have that kind of probability density functions. Out of that, we can get some data points. We sample it We sample data points from the models. We sample data points from the probability density models. In these directions, we call it probabilities. So in summary, statistics, starting from the data, we're trying to build up the models. As opposed to probabilities, given models. We want to produce or we want to generate the data points, samples. It's all about the probabilities. Okay, so always it's these two, the statistics and probabilities are like compensate each other. So in these directions, we're talking about the statistics. In the other directions, it's going to be probabilities. So let's focus on statistics first. So in order to discuss or talk about the statistics, there is some terminology that you have to know. So the first thing is populations. I mean, we use like how many populations in Korea. I mean, we use populations in common conversations, but in the sense of statistics, we call it populations. There's a specific, it has a specific meaning on that. And the second, samples. How many data points? How many samples? But there's very specific meaning there is in the sense of in terms of in the discipline of statistics. So formal definition is that formal definition of populations in statistics includes all the elements from set of data set. I would say entire data points, entire data set. Right? That's populations. And okay, that's the first one. And I'm going to skip that one, but I'll revisit. And the second terminology that we have to know or we have to understand is samples. It's subset of populations. Subset of the populations. And it could be one or more observations, or I would say data points, but observations. Okay. So suppose we have, say this is in the entire set, I'm going to say it's populations, and this part is subset of this, so we call it samples. You might have some finite number of, I would say data points or observations. Either way is fine. Okay. And as you can see, the ultimate goal of statistics, I would say, from samples, want to estimate some properties of population. Right? That's the common. I mean, that's the purpose of all about the purpose of statistics. With the limited amount of observations, we call it sample. We want to predict, or we want to estimate, or we want to know, or we want to understand entire population. I mean, any kind of properties of entire population. That's the ultimate goal or purpose of statistics. Okay, I think that's super clear. And let's get into more more details. And for populations, we have parameters. That's a quantity computed from the population. So we have parameters. Some of the example of parameters, probably mean or variance, mu or sigma squared. If we have populations, if we know, then we can compute, we can calculate mean of that or we can compute the variance of that. We call it parameters. On the other hand, for sample, again, it's same. The quantity computed from the population is quantity computed from a sample. We're not gonna say we're not gonna say parameter. We're gonna say statistic. Okay. So any quantity we computed from, it's a statistic. Of course, there's some data points, right? Observations, we can compute mean and variance and covariance, whatever. But since it's a statistic, we call it sample mean, we call it sample variance, we call it sample covariance. Okay, so and probably it's x hat or s squared, or it's covariance between the random variable x and y. We call it s of y. And the meaning of covariance, actually, I don't think I explained it. I covered the meaning of covariance in these lectures, but we're gonna talk about covariance in a minute. But mean and variance, you guys already know. We learned like from high school or like freshman or software, whatever. I mean, I'm pretty sure that you guys already have clear understanding of mean and covariance as well. But the covariance probably I will revisit to discuss. So again, I said the goal of the statistics from the information of samples, we want to estimate any kind of properties of populations. In other words, from statistic, we want to estimate parameter. Does it make sense? So from statistic, we want to know parameters. Here we use statistic. Right, so specific meaning of statistic. That's a quantity computed from the sample, not from the entire population, right? So those are the basic like terminology or concept that you have to know, or you have to keep that in your mind. And because we're talking about the data points, observations, and populations, things like that. And because we're gonna use computer, so I want to let you guys know how to generate random numbers, assuming that these generated random numbers could be entire populations, or could be the sample, a finite number of observations. Okay, so how do you generate random numbers? Data sample from populations or process or generative models. So I'm gonna say again, here is how to generate random numbers. It's a data points, observations sample from populations or process and generative models. In this slides or throughout these lectures, I'm gonna use, sometimes I'm going to population, sometimes I'm going to use process, sometimes I'm going to use generative models. All of them are the same meaning, and this in these lectures or semester. Okay, something is true process or true populations or true models. But only thing that is only information or data points available could be finite number of observations. We call it some finite number of data sampled from true process or true populations. Again, it's going to be sampled. Suppose, like for example here, say M is number of probably like sample size or number of observations that we have, like 1,000. And we have to define populations or generative models, things like that. And the true, like, if we think about the probabilities, the true model is one of the ways that we can define the true model is probability density functions. Here in this case, we can use uniform distributions, or we can use, let me see, like here, uniform distributions, and here it's Gaussian distributions. I'm going to give you or show you two examples of probability models. And Python, we have random.rand. Okay. And the only difference is that np.random.rand n. You guys can guess it's normal distributions. Gaussian distributions and normal distributions are the same. So rand is uniform distributions. Rand n is normal distribution or Gaussian distributions, you guys can think. And here is a number of observations that I want. Let me see. And here probably is given uniform distribution is uniform distribution between 0 to 1. And that's the number of data points that we're going to generate. So here it's observations, 1,000 observations. The sample size is equal to 1,000. And then next thing is that you guys might think that, hey, I want to generate uniform distributions, but not from 0 to 1, from like A to B, right? Then in Python, it's not going to have other uniform distributions, but the idea is that we can utilize these things to generate another uniform distribution from A to B. How? As you can see, if you A, okay, so let me say it's from A to B. And suppose you have 0 to 1. Okay, so the length is 1. And over there is length is B minus A. Suppose that's all of them are positive, things like that. And then we can just multiply it. And since it just shifted it, so we add that. So this is typical trick. So now you can generate any uniform distributions. You can generate the data points, random numbers or data points or samples, at least uniform distributions, you can do it. Okay, let's do similar task. In this case, in terms of normal distributions. And again, in Python or any other numeric or scientific language of programming, this is Gaussian distributions, mean and the variance or standard deviations. We call it standard normal distribution or standard Gaussian distributions. There's some embedded random number generator, like as a function. So we can generate it. But another or same extension that we have to think about in this case is I want to do, for example, that's another Gaussian distributions with mean of 5 or the standard deviation of 2. Then Python does not have the direct functions to generate it. Doesn't have like random generator, but we can utilize these things. How? Okay, again, it's 5, and we multiply by 2. Because here 1 and 2. So that's how we generate any normal distributions. We can generate any Gaussian or normal distributions from standard Gaussian distributions. You can use that things. Okay, so that's, I mean, I did in order to, I mean, how I showed you how to generate the random numbers, and this is only 2 examples. And sometimes you have to generate another data set followed by, I mean, given by another probability functions. Then you can Google it, and I guess either MATLAB or Pythons, any kind of scientific languages, they have embedded functions, and you can utilize that one. So for random number generators, you guys don't have to worry about anything. It's available, and you can use similar patterns or tricks that I demonstrated here, that I showed you guys here. So now suppose you have some sample or observations. I would say there is some data set, some data points. And the first thing probably you might want to do is that make histogram out of data points. Histogram. How you do that, you already know. I mean, suppose there's some data points in the range of that, and they say 0, 1. It doesn't have to be zeros, but for example, like 4, 5, 6, things like that. And you have to make some bins. Like that. And out of observations or data points, it doesn't have to be entire populations. It could be subset, which is sample. And you want to count it. How many data points belongs to in this bin? You count it. Counts or frequency, right? And you count it. And next thing is that from 1 to 2, those ranges, like also you count it. By doing that, what you did, you just create, or you just make or draw histogram. This is graphical representation of data distribution. You can see that, okay, the data points or that I have, or the data points that are given is kind of have this kind of distributions, data distributions. I mean, it's rough sense of density functions, not the exact, but I think it's okay. I mean, as you can see that if you have different length of bins, right? It really depends on how many data points you have. It really depends on, but it really depends on your application. It really depends on either number of data points are available and the length of bin that you want. Specifically, you want to be like the length of bin of interest. Okay, but I recommend you that, because we're talking about the statistics. Whenever you have the sample or whenever you have some observations or data points, please remember that first step you have to draw the histogram to get a rough sense of your density of functions. Okay, that's why I'm going to say histogram is so important to get rough idea of data set that you have, or data set that you suppose you're going to deal with. Okay, so next is inference. Probably this is might not be familiar with you guys, inference, but there's, in the sense of statistics, there is specific meaning of inference. So that's we're going to discuss. All right. So true populations or true process or true generative model, in many cases, is going to be modeled probabilistically. You guys know what I'm talking about? Say this population is followed Gaussian distributions or normal distributions or uniform distributions or any kind of distributions. Okay, that's one way that we can model for true populations. And the sampling means we're gonna have finite observations. We call it sample, right? And by doing samplings, that's gonna supply us with realizations from probability models. So be careful on the realizations, okay? So suppose we have true populations. There's a lot of uncertainties and noise, and it's all about I'm talking about the probabilities. So close your eyes and just take some finite number of observations. We call it samplings. So we got some finite number of observations. Here I say realization. Why? Because if I do that again, it's going to be random samplings. So if we do that, if we repeat that process, we're not going to get the same realizations. I mean, same data. We're not going to get the same, in general, we're not going to get the same data points. So the data points that you have right now, it's one realization. So in the next time, probably you're gonna get different data, one different realization. So in the statistics, the sample data point itself probably doesn't have that much like importance, because next time probably we will get the different set of data points. But in these data points probably has important information of true population, distribution of true populations. You see what I mean? So to compute something, but we have to recognize that we have just easily gotten a different set of realizations. So again, if we're doing different sampling process, we're gonna get different set of realizations. But the pattern of realizations, so hidden pattern, gonna be pretty much the same. But the actual number might be different. Actual number of data points, okay, realizations might be different. I mean, it should be different because we're going to do random samplings. But the pattern or some kind of, I would say histogram. Okay, if we do most of things properly, the histogram or pattern or distributions gonna be pretty much I would say similar. I'm not gonna say they are the same, but it's going to be similar to each other. That's the key concept the concept you have to keep in your mind whenever you're talking about the statistics and probabilities. So I guess here the pictorial illustration is extremely, I mean, I guess it's useful. I would say this is true populations or model, generative models or process and any kind of probability density, whatever. I mean, this is true. Okay. But the problem is it's unknown. It's unknown. I mean, there are many cases that the true populations or process actually is like sometimes in a lot of in many cases it's unknown. It's too difficult to figure it out, whatever. So there's no way that we can figure it out or we can understand or know the true process. And that's the first case. In the second case, say it's populations, but in like with some kind of technical issues, probably like if you measure the entire like data points for the entire population is like too expensive or it's like time consuming, whatever. In that case, it's unknown. So there are many reasons, but suppose that don't worry about the existence of true populations, but there is true populations, but with many reasons that there was the true population is unknown. In that case, what we can do, we're gonna do sample. We're going to do sampling process. So like I said, this is like some kind of screen and it's not transparent. So we guys are standing right here. So we cannot see true populations, but only information available is we're doing like random samplings. So we have some finite number of observations. We call it sample. So here, like for instance, in this case, we have only 5 data points that's available to us. Only 5 data points. I mean, in this case, it could be like 100 or 1,000 data points, 1,000 observations. We call it one sample. That's the situation that we have, that we are facing. And again, the purpose of the statistic is that with these limited amount of data points, but we want to know true process. We sometimes based on this, we want to estimate it, or we want to make some kind of conclusions on populations. We call it, in those processes, we call it inference. We want to do inference with quantified uncertainties, with finite number of samples, finite number of observations. It's all about the inference. That's all about the inference. That's all about the data statistics. That's all about the machine learning. And think about the regressions, or think about the regression problems. Yeah. Okay, so like linear regressions. See, I mean, these are the given data points, training data, whatever. It's finite. We will say like was 13 data points, and these are sample that we have. It's one realization. And there's no way that we can know the true populations. And but what we did in the regression is that with this, we did inference. We did that. Probably this is, I'm not sure it's the best, but I believe that it's okay models. Okay inference. So assuming that this might be, or nobody knows, because nobody knows the true process. But at least we want to believe that it's okay. Okay, that's the inference. So classifications or regressions, all the things that we learn so far is part of inference in a sense of statistics. And let's move on, or let's, so suppose, I mean, here in the same framework, we have true populations. Again, we're gonna assume that it's unknown because that's the in common case. Suppose we have random sampling, so it's one sample. one sample is not one data point. It's a set of observations. We call it, that subset of the, we call it sample. So it's a subset. For example, like we have like 10 observations. Okay, it doesn't have to be 10, but it's some observations. We call it subset. It's one sample, and we can repeat that sampling process, random sampling process. So we have another samples and another samples. Okay, and then out of that samples, we can compute some quantities that we can compute it from the sample. We call it statistic. I mean, for example, it's mean or variance, whatever. And just for simplicity, it's just assume that everything that we want to compute the mean or average mean. We want to compute the mean value of that. So here, suppose we compute sample mean. And say it's 10 data points. And the sample mean is 1. Right? Because 10 observations, we're going to compute one value, which is in this case, it happened to be sample mean. Okay. Suppose we have, we say like how many? Like 100 samples. Then, which means that we're going to have 100 sample means, right? Let's say X. Then I want to know the distribution of sample means. Then the easiest thing is that we can make histogram out of it. This is a histogram, it's a sample distributions. So that's what we can do. This one is represent the histogram of sample mean. Okay. Here, because we know that we assume that the existence of populations, that means although we have no idea or the true population is unknown, we know the existence of parameter, which is mu in this case. But thing is, we don't know because we don't know about the populations. But here, at least we can get sample mean. And if you repeat many things, we repeat it, then we can get histogram of sample means. And the question that we have, there's no way that we can figure it out mu's, but we do have this kind of distribution, kind of distribution of sample means. Do you think mu and x hat are the same or different? That's the question that we have, or statistician that they have. So how can we get mu or estimate or predict out of sample means? That's all about the inference. Okay, so I guess you guys take some time or moment to visualize this process. Visualize this process. And in the challenges in the real life is that here we repeat the random samplings like many times for instance, here is 100 times. It doesn't have to be, but say, so for example, it's 100 times. But in some case, we want to infer characteristics of true population or true probability model from one sample, like that, like that. Say you got 10 observation, and you can compute mean. Here in this, the histogram, we don't have. Only thing is that the value that we have is this one. The only value that we have is x hat. And how do you relate it? The statistic from only from one sample. How can you get the uncertainty of this compared to true population of mu? That's the challenge that we have for inference. Okay, but actually this is the problems that you're going to face. You have only one sample. And you can compute statistic. You can compute the sample mean, or you can compute sample standard deviations, whatever. And we are not sure about that the statistic from sampled. How do you relate it to or how do you make good inference of parameters of true population? Okay, that's kind of the things that we have to keep your mind or consider or think of. Okay, so now I think it's as you can see in the title is it's a law of large numbers. Probably you guys already know and you is familiar with and you heard many times. And what the law of large numbers says is that now all the framework that I discussed so far utilize that things, and sample mean, which is like that. Sample mean. Again, all the inferences. What about? From that one, I want to. What the law of large numbers that if as sample size gets large, M, this guy converts to that of true population. What do you mean by that? Here it's the sample size. I'm gonna increasing it. That means you're gonna have more observations, and we're gonna compute, right? That this guy gonna converge to mu. I guess this it makes sense, right? In theory, so mu gets larger and larger, then at some point it's going to reach the number of populations, right? That means we just gonna take the entire data point, entire population. So in that case, sample mean is same as the mu, which is parameter of mean or populations. So that's why based on the law of large numbers, it's extremely important to always whenever you have a chance then it's always good or better have large number of sample size. It's too obvious, right? But in a practical sense or technical issues, getting the data points or collecting or gather the data points probably it's extremely expensive or costly. So that's the limitation that we have. But at least in the perspective of statistics, always for the samplings, do as much as possible, as many as possible. Then sample means gonna get closer to mu. Right? Sample variance, right? S close to sigma, things like that. And let's see sample mean and sample size. Now we have M is same. I mean, I use M to represent the sample size, the number of data points or number of observations in one sample. You could say, I mean, this is the formula that we can. It's a sample mean and the sample variance. Okay. And one thing that I want to mention here, in, let's say, let me see, for sample variance, we do, right? How many data points? Here, M data points. So I guess 1 over M probably, but here, as you can see, it's M minus 1. Why is that? Why is it? I mean, this is correct. This is not correct. So, okay. So for this, in order to explain, there are many things that we have to cover. But again, I don't think it's not that important. But key thing is that if in that case, suppose we know the true mean here, then this is correct. But the problem is we have no idea on mu, right? So instead of having mu over there, the only thing that the best approximate that we can is this one. This one. Okay. In that case, if you do some the math or calculations, you end up having 1 over M minus 1. Okay, just remember that. I mean, you don't have to understand it. That's okay. That's totally fine. But in here, the sample mean or sample variance, that this is the right formulas. But keep that in mind. This is M minus 1, not instead of this, not M. Another thing, the second thing that I want to here, suppose that your sample size is 1,000 or 100. Then here is 1 over 100. Here is 1 over 99. It doesn't matter that much. Okay. So that's why it's not that important. I mean, in statistics or mathematically, in order to be very strict, and this is 1 over M minus 1. But I mean, as sample size gets larger, it doesn't matter that much because it's going to be like approximations, right? That's the second thing that I want to mention here. And I'm going to move on. Another theorem that you have is central limit theorem. Central limit theorem. Okay, what the central limit theorem tells us is the sample mean, not samples, okay, or not observations. Probably say not observations. I would say sample mean here. This one. We have samples. We compute, say is mean. The sample mean, and we can get histogram out of it, will be approximately normally distributed. Gaussian distributions. So what I mean by that is that if you make histogram of a sample means, eventually it's going to be Gaussian distributions when as sample size gets larger. It's like, I mean, it sounds like easy, but it's not that intuitive. It's not easy to prove. It's not easy to show. Why? Because this central limit theorem is true regardless of any distribution of populations. The distribution of population doesn't have to be Gaussian. That's the key. That's the key. It might have different distributions of there. Again, doesn't have to be Gaussian. Doesn't have to be Gaussians. But if you do random samplings and the histogram or distribution of sample means is going to be Gaussian distributed. That's the key. That's the key. Why is that so important? I said it's unknown. Sometimes you might know the true process, but sometimes really nobody knows. But the good thing about central limit theorem is we don't have to know. We don't have to know true distribution of populations. It doesn't matter because of these central limit theorems. We know that this one is going to follow the Gaussian distributions. Wow. Wow. Again, in these lectures, I'm not going to prove, I'm not going to show it, but just take that for granted. Okay. But there's some condition that we have, the sample size. Again, we have to have large number of data points observations. That's why probabilities or statistics or machine learning, whatever, if you're talking about data, the first thing is that you have to securely, you have to have big data set. You have to have a big data set. There are a lot of like large number of laws and central limit theorems, and all these theorems the fact that you're going to tell us, they say you have to have large number of data points. The sample size, whenever you have a chance, you have to get the more data set. Starting from that big data set, any kind of data analytics has higher confidence on that, because you know that in that case you have your inference going to have as close to true parameters of the true populations. Okay, inference, whenever you have any information that you're going to extract from the sample, you might have uncertainties you are not sure about, or uncertainties or the confidence that you have. So if you have increased number of the sample size, you might have higher confidence on this. Okay, that's the key concept that you have to have in your mind. Okay, so let's move on to uniform distributions. And what I did is that we have the sample size 100, and I did that, and I generate random numbers, and this will be 100 observations and one sample that we have, and X bar is sample that we have. And actually we have in the Python mean, the function is embedded, so we can use that. And as you can see, X bar and the means, it was the same. and variance bar, and we have the embedded functions. As you can see, I did 1 over n minus 1. So we get this. I mean, let me see. And variance and slightly different. Oh, okay, I see. And I guess, let me see. Here, this is the sample variance, and the variance, I mean, was slightly different from. I'm not sure, but I want you guys to check whether this one is different. So try that one. This part to see if it will get the same thing or not. Okay, but again, it's not that important. I mean, pretty much it's both of them are good because anyway we're gonna do approximations. And in order to see the importance of sample size, m is from 1, and here is from 10 to 2000. I increase by 20. Okay, and as you can see, m gets larger, and the sample mean gets closer to true mean. That's kind of, these are the data points, and eventually getting closer. Like this is kind of numerical example that I can numerically show, not prove for the large number of law of the large numbers. And let's talk about the central limit theorem. And the variance gets smaller as right. As, let me see here, and we have m, and let's see, for samples we have, for samplings we can have 10 observations, or we have sample size like here. And it seems that, let me increase that, the histogram looks like, I mean, it's getting closer to Gaussian distribution. I mean, in this, the numerical examples is not that easy to see, but like based on the central limit theorems, seem approximately Gaussian distributions. And another thing that I forgot to mention is that the sigma, the confidence, I mean, it's you know, the Gaussian distributions and how spread or how narrows, right? So as you can see, if we increase the sample size, gets smaller, as that means we have higher confidence on your from mu. And for that expression, I guess it's kind of vague, but I mean conceptually, I think it's just take it as a sample size gets larger, the distribution of sample means going to follow the Gaussian distributions, and at the same time, because what we want to do is we want to inference from the sample mean to the mean of true parameters, right? The mean of true populations. These are the uncertainties that we have. But we know that the distribution is getting tighter. That means you're gonna have less uncertainties. At the same time, you're going to have higher confidence on your inference. That's the things that you're supposed to remember. And what I did is that instead of doing some kind of the proof, I'm just showing that with the numerical examples that we have. All right. And this, so far, in order to explain the basic concept of statistics, I only use one dimension, like simple case. But as you in regressions, like we starting from single variables to multivariate case, we can do the same thing. We have to do the same thing here for the statistics. We call it multivariate statistics. Multivariate statistics. Suppose we have m observations. Now we have m, not m data point. Now we have m vectors. M vectors. So we have m vectors. We can have, say, d. Suppose in d dimensions, then we're going to have column vector with d elements. That's one observation. I mean, I guess it's not that difficult because, I mean, in the regressions and classifications, we quite use, I mean, instead of single data points, we're talking about the single column. Now we can define the sample means and sample variance in the multivariate statistics as well. Now this is vector. So sample mean also is like another column vector. Sample variance is going to be D. Okay. So now, starting from single variable statistic, now we move to multivariates. Now the only difference that we have is starting from scalar now is everything is column vector. I think which is okay, you guys. But another thing that we have to think about it, another concept that we have when it comes to multivariate statistics. This one, the first element is sample variance of first data points. These data point, right? And here, the second element is sample variance of these. You see what I mean? Now I want to find out the relationship between the other variables. So suppose the relationship between, we cannot get relations among 3 different random variables. So let's focusing on the relationship between 2 random variables. We call it correlation. We call it correlations. And the sample variance, we already define it. Sample covariance, we can define, let's say we have X and Y. We want to know the relationship between them. One of the definitions that we might have is we just multiply by and take the mean. But the thing is, X random variable and Y random variable might have different means. So in order to make fair comparison, probably what we can do is we just take mean of each, and we do multiplications. So suppose we have only 2 variables. Okay, then this is sample covariance, and we can extend it to sample covariance matrix. Why is that? Because we have X and Y, right? And we find out, sample covariance between X and X is the same as sample variance. And I want to know covariance between X and Y and X, and Y and Y. So we This is the notation that we have. Probably I will say it's x and y, and it's y and x. But here x and x is like the covariance x itself. So in short notations, you can say x and y, it's the same. And another thing that we can say, this one and this one are the same because relations between x and y and relations between y and x, it's a symmetric. It should be the same. So the sample, which means that in other words, sample covariance matrix always has to be symmetric matrix. Symmetric matrix. Okay, that's the formal definition of sample variance and sample covariance and sample covariance matrix. And don't forget that we have to take the mean out before you do multiplications. Okay. Another thing is that here is a covariance coefficient. Why is that? Because maybe x and y, the scale might be different. So what I want to do is that I want to normalize that. I want to normalize them to make fair comparison. Okay, so that's the definition of covariance matrix, and correlation coefficient is, say we have x and y, like that. Then probably I will divide it x and x and x and y. It's kind of normalizing it. It's kind of normalizing it. You guys see what we are doing it? Okay. Now, let's see the definition of correlations or meaning of correlations. This means that so far what I did, I said is I want to find the relationship between x and y, between random variables of x and random variable y. What kind of relationship? Be more specific. The covariance gives us the information of strength of linear relationship between x and y. Remember, correlation gives us the relationship of linear, how strong, how the between like two random variables, x and y, how strong have linear relationship between them. That's the information that we can get out of correlation. Okay, the correlations, we can compute the correlations, that the correlation value is going to provide for us the information of strengths of linear relationship. Okay. So in order to see the correlations between two random variables, the experiment that I conducted is that suppose we have two random variables in x and y. We have n data points. And randomly generated x and y's. And we reordered it, sorted by like that. So imagine that you have m data points, x and y, randomly generated, because you guys already know how to generate random data points. Now, because we know the magnitude, we can rearrange it like that. Now what we can do, we can pair it. So these are the data points in two-dimensional space. Or we can do, so this is the smallest one, and here is the largest one in y and smallest in x. And keep the orders and I will swap it. We can do that, right? Or or just randomly select. This is first and second and third. If you plot them in two-dimensional space, this one, because we know that if x gets larger, we have a tendency of y values gets larger as well. If you plot it, you're gonna get this kind of distribution. Does that make sense? In the second case, we know that gets larger and gets smaller. Gets smaller. Then we're gonna have this kind of distribution. Okay, and if you just pick random combinations, I mean x and y, I mean has nothing to do each other because we randomly selecting, and if we plot them, you're gonna get this kind of data point distributions. Okay, does it make sense? What we can do is that by looking at this, we know that this is the data points we generated. That means that if we have x and y, if we know the x, we kind of get the idea of y. Like that. If we have higher value of x, it's have like y. And we can make same conclusion on this. Have higher value of x, we kind of know the tendency of y, the way y values get smaller, like this. Which means that the information of x gonna help us to estimate the value of y. Either way is fine. So in statistics, we're gonna say statistically dependent x and y. Here, x and y are statistically dependent because either x or y, the value gonna give us hint. But in this case, it's unrelated, has nothing to do each other. That means statistically independent. If we have two random variables, it turns out these two random variables are statistically independent. That means by knowing the value of x, it's useless information to estimate the value of y. Okay. And how, if you compute the correlation coefficient is equal to 1, that means that like that. Or it does not give us the slope, information of slope, but we know that it's strongly linearly related. If like say, then in that case, probably data points is like that. I mean, you can try in using the Pythons to see what kind of data distributions that you're going to have when you see like correlation coefficient 0.9 or 0.8, things like that. You can try, see if you get some ideas. And if the correlation coefficient is -1, that means we have negative slope. But again, it's a strongly have linear relationships, and like -0.9, that means like this kind of distributions. But remember that statistically independent zeros, and you're gonna have in Euclidean distance, you're going to have like this kind of distributions, like Gaussian or like circular distributions. If you're looking at the data points from top view, right? So correlation coefficient, again, is if +1 is close to straight line, -1, again, is close to straight line. The correlation coefficient does not give us the information of the slope. It only indicates how close to linear line, but it's no information on the slope. Okay, if the absolute value of correlation coefficient is close to 1, that means linearly correlated. Is close to 0, that means uncorrelated. Uncorrelated. I guess now it's clear to everybody. And another thing that I want to mention before I close this lecture is that suppose we have two random variables, x and y. We can compute the linear. I mean, we can compute the correlation coefficient. But say its correlation coefficient is 1. It does not tell us anything about causality. We are not sure about. This one means that if we have like x increase, y increase as well, but we don't know which one is causal and which one is result. Only thing is like this kind of behaviors. So the reason that I will mention is causality is that many people got confused whenever you compute the correlation coefficient. They believe that they might have x and y some kind of causality relationship, but it's not. Okay, that's side note. So that's actually what I hear. The experiment that I did here is that actually I used that in Python here. If you sort it out and ordered or reverse orders and plot it, as you can see, this is random data points and sorted it. You have positive, like linear relation, kind of linearly strong linear relationships, and reverse ordered we have negative, like that. That's kind of numerical demonstrations of the correlations or correlation coefficient. And again, this one is the in y, we in x I double it, right? But as you can see, the correlation coefficient or matrix, both of them are. I mean, this is almost zeros and almost 1, and here is almost zeros and almost 1. So again, the thing is have no information on the slope. It only indicates how close to linear lines. I mean, both of them are linear lines, right? The slopes are different, but we don't have the correlation coefficient doesn't give us any clue or any information on slope. That's what I want to, the intention that I have for using the numerical examples or demonstration that I have. All right. And because again, whenever you have multivariate data points or features, whatever, the first thing is that you have to figure it out. You have to know plot and you have to know correlation coefficient. But thing is, suppose you have 3, like x, y, and z, and correlation coefficient is only relationship between 2 random variables. So the combination that we can make is that we can have like that and like this, right? We want to find out the relations x and y and z, and x and z. And we have 4, then we have to have another combinations like that. So in that case, suppose we have x and y and z and w, and x and y and w and z's. And this one is we plotted x and y. This guy we plot x and z and w's and plot them. And this guy is we plot x and y. So I guess probably these are kind of symmetric. So actually these this is kind of redundant, but it's okay. And x and x is always the correlation coefficient is equal to 1. So it doesn't have to compute it because it's right, the relationship by itself. So in that case, we plotted the histogram of that, which is give us another information, right? It's good. Now, the thing that we can have is that out of this, probably x and y is uncorrelated, x and z uncorrelated, x and omega is uncorrelated. This one, y and z is highly correlated, y and omega is highly correlated, and z and omega is highly correlated. Right? Those are the first information that we have to get whenever you have multivariate random variables or the variables that you have. And actually, this is very extremely useful graph plots that we have. So in Seaborns and SNS and Pandas field, whatever is this single command, pair plot, you guys can, Python is going to plot this useful information for us. Okay. So again, correlation coefficient plot, that's the first thing that you have to do whenever you have multivariate random variables. Okay, so and correlation covariance matrix in the statistics, probably you have to compute like that. But in probabilities, actually, I mean, here is, I will say, optional. We estimated these two random variables, we estimate expectation. And this is kind of, this guy is kind of, this is, we can get sample covariance from statistic perspective, and from probability perspective, covariance matrix is, suppose we know that given, if we know the given probability density functions, probably we can compute expectation of. Okay, so these are kind of from probabilities, and the covariance, sample covariance matrix is from statistics. And these two have, if we have large size of the, and this guy is gonna have good approximation of covariance matrix, right? With that, that's, I think it's all the materials that I have for statistics and probabilities. Again, I mean, this is not the statistics lectures, and I only cover some of the useful concepts or materials in statistics for better understanding of machine learning. Okay. And with that, probably next time I'm going to do principal component analysis, which is gonna use the covariance, like a sample covariance matrix, the concept of covariance as well. Okay. So with that, I'm gonna finish it up.